decision process is very simple. Like the whatever our intuition says, it is the same way that every node you check the attribute value. So every node is characterized by an attribute. Every node, every intermediate node is characterized by an attribute, and a leaf node is characterized by the corresponding output value. That means corresponding output levels. So you can see all the red colors, they are representing leaf nodes, and there are classes, uh, class levels which are represented by them. So leaf nodes are characterized by classes. So they are the answers. And whereas in a decision tree, given a input instance, given any input vector, the instance itself, so the corresponding attribute values will be checked in a sequence. So for example, it will start from the root node, and then it will check whether the attribute, what is the attribute value of sky. So if the attribute value of sky is sunny, then it will take the leftmost subtree. It will take the leftmost subtree. And otherwise, if it is overcast, it will go by the middle subtree, and it is understood. Then the rightmost will be rain. So there are three attribute values are available for the attribute sky. Fine. So depending upon the value of the sky, or we can say outlook, that was also name of the output attribute. I mean, we put it here, sky condition. Then we would be going through some path of the tree, and we'll go down to that path. That means the next intermediate node will be checked. For example, the value is sunny, then the next intermediate node will check the value of humidity. So from that same instance, and it will find out now what is the humidity value, and we consider that there are only two possible values, and that's why there are two branching there. And depending upon that value, you get the answer. Either it is condition is yes, which means no, it is representing the target function evaluates enjoy sports levels. So yes means yes, condition is favorable for the sports, and no, it is not favorable. So this is what you are doing. So just to summarize, to understand the structure, that each internal node you are testing an attribute, and using that value, you are following certain branch and certain subtree along a path, and then you just go down following the same mechanism. That means you find out what is the node and what is the attribute value it should check, and you go down to the leaf node, and you find out what is the level of the leaf node, and then you classify. Uh, Actually, in the last class itself, I mentioned that this tree structure is also representing a Boolean expression. And if I consider the same kind of representation of conjunctive normal form in the previous case of representing a Boolean expression, here it is the disjunctions of all those conjunctive forms expression. So every path will give you, every possible path will give you a conjunctive form, and then all of them should be ORed to get the expression. So this is the logical formula. Like if I consider our expression considers these are the position, that means sky conditions, then I think then should be temperature maybe, and then humidity, and then wind speed. So if you look at the and only you will be checking the yes conditions. So you need not consider any path which will go for no, because that is your contention that if this expression is satisfied, then actually the value is 1, otherwise it is 0. So only Boolean expression, you know that you have to consider the whether the expression is satisfied or not. In that is what you will be expressing there. So there are 3 yes conditions. Yes, there are 3 paths corresponding to yes levels. So for each path, you have these expressions. So do you have any questions on this particular structure? Okay, so let me proceed in that case. Yeah.
I'm a little bit confused about the leaf nodes. Sir, what is the leaf nodes? These are the red colors, those red color values are the leaf nodes, or the high, normal, etc. are the leaf nodes?
No. High, normal, they are the age levels. Okay. High, normal, they are the age level. You see that each branch corresponds to attribute value. So if the value of, for example, you start from the root node. So if the value of sky is sunny, then it will go through that tree following that age. So every age is now characterized, is labeled by the corresponding attribute value. Is it clear? So node represents a attribute which requires to be tested, and age represents the test result. So after the test, you find out which value it is. It will go through that particular path. And then when you come to the leaf node, then you get actually output levels. So leaf node contains the output levels. Intermediate nodes contains the attribute name for which you will be computing, you will be doing the test. And ages are labeled by the corresponding attribute value through which you will be doing the branching. I hope now it should be clear to you.
Yes, sir.
Okay. So, and the logical expression, is it okay?
Yes, sir.
Fine. So let me then proceed. And you see that decision trees also, it can be considered that no, it is a set of rules. It is representing a set of rules. So each path corresponds to a rule. And it is basically any of these rule, if it is satisfied, any of the rule, if the condition is satisfied, then it's an implication rules. So it says that, see, if outlook equals sunny and humidity equals normal, then you should play tennis. Or if outlook equal overcast, then you should play tennis. Or if outlook equal rain and wind equal weak, then you play tennis. So you can represent this rule in a much briefer form also. But no, finally from a decision tree, you get a set of rules. So what are the, when should you apply decision trees? Now, what are the context? What is the context on which this decision tree kind of classifier is more relevant? So one of the things, as you can see, that it is every node, you try to see that there is a finite option of branching. Otherwise, no, you will have infinite branches, and that is not feasible. That is not tenable. So that is the kind of assumptions. That is the kind of constraint that you consider that your input instances, they should be describable by a fixed set of attributes. That is the first thing, and also their values. So you have a finite dimension of your input space, and also every attribute also should have a finite set of discrete values. And then now target function is discrete valued. It could be two-valued function and so what means discrete value? That means values are also, that means output values, they are also discrete levels, right? So it is not any continuous, you are not. So the function form is that you are mapping an instance. You are mapping an instance to a range which also is a set of some discrete values. So instances are described by, once again, a fixed set of attributes. So instance is an element of a finite dimensional space, and again each attribute also has a only they have a fixed set of values, right? So but your output could be also invalid. That means it is not necessarily that, no, the example what we have considered here only two-valued examples. That means it is either yes or no, or 0 or 1, whatever way you describe, but it could be multiple levels also. So you can have decision tree for multiple levels. And also, though we have considered the case that no, your attribute should take only discrete values, but no, you can consider also continuous functions, but you have to approximate, you have to discretize it into a finite set of values. So that is the thing. By doing that, no, you can handle continuous functions. And your hypothesis space is in the form of a disjunctive hypothesis space. You can handle noisy training data. So it is possible to get a decision tree which will give 0 training error. That means you can get a consistent hypothesis. So if you consider a decision tree, I mean, that's an hypothesis, that's naturally. So you can get a decision tree which is consistent with the training data. Okay, but again, you may get agnostic hypothesis also. That means no, you may consider to get some noise. You can allow certain amount of noise. So that is also possible using decision tree structure. So like you can handle errors, you can handle missing values. We'll come to those things when we discuss about in details of this tree construction. Some of the examples of its applications, you have those diagnostic decision support systems, diagnostic rules, where decision trees are used or they are learned. Any question? Can you repeat the question? Is not audible, or has anybody tried to ask anything? Mm. Is there anyone? Any question? Someone's microphone needs to mute it. Huh? So you have these other things like credit risk analysis, calendar scheduling preferences. These are various kind of applications. Now, one of the simple examples, I just mentioned it in my previous class, that is the learning of rectangles, where you consider your instances, they are bounded by certain rectangle in the corresponding instance space. And if you get those examples, and your objective is to get those rectangles which include only the positive examples, that means in which interior positive examples lie, and that would be your hypothesis. That means the test will be that given a new instance and given its values, like here we have considered two-dimensional instance space. So we have two attributes, attribute 1 and attribute 2. And given their values, you find out whether that point lies in any one of these rectangles. If it is lying in one of them, then you say that it satisfies the condition, and no, you say it is a positive example. So one of the way you can have a bit more visual, some kind of visualization of this formation of decision tree using this example. It's a nice example. It's very simple. So you have to rather take a decision on the attribute values. So you see that here attribute values we may consider they are continuous, right? And but what you can do that you can consider certain. So you can also consider they are discrete also. It doesn't matter. So at each discrete intervals you have the attribute values. So whatever may be, so you have to find out certain attribute values where you can split the regions. That means you have to draw axis parallel lines. So for example, this is one axis parallel line which divides the input training examples. These are the training examples in the input space into two hubs. In one hub, you can see some samples lie, and incidentally, it happens so that if I consider the left hub and right hub, the left hub is a hub here which contains the origin of the space, and say right hub is the hub which contains the corresponding positive examples. But you understand that from the geometric computations, it is a representation of the straight line in a coordinate space, which will finally define the left half and right half plane. So I'm not going to detail out all those things. No, you need to go through a book on coordinate geometry, and you should brush up and check how left half plane and right half planes are identified. Given a straight line representation, given a line representation, for example, given 2 points, you can represent a line, and using them, how do you represent these different hubs? And in one hub, so given any point, you can test in which hub it is lying. In this case, it is very simple, of course. Since it is axis parallel, you consider whether the value is greater than certain value. So, which means in this case, let me use a pointer. Say this is the value. This is the value on which the split took place. So, for attribute 1, and you can see that it is using attribute 1 because this line is parallel to the attribute 2 axis, and it is actually the test is done using attribute 1. So the test is something like this. Suppose this value is, say, x, right? This value is x. So if attribute 1 is greater than x, so this region is, say, greater than x. So if it is greater than x, then we consider this is that region. And if it is less than x, this is that region, right? So this is the two splits. I mean, this is the splits that you can do in the input samples. And as you can see, of course, in this case, all of them are positive. So probably this should be a leaf node where you have reached a decision. But since still this is a mixed region where there are positive examples and also negative examples, so you require more splits to bring it into this. So let me proceed, and things will be more clear to you. So, for example, you have a split here. How do you find it? Let us not discuss. There is an algorithm by which you can find the positions of split given an attribute. But in this case also, you can see that you are using still attribute 1. It is not that you have to use attribute 2 because you have used earlier attribute 1. It is not like that. So only thing is that given the input set conditions, that means when you have started with initially the whole input sample space was considered, this whole training example set. Given that set, you have determined that it has to be, you have to choose the attribute 1 for the test, and you find out that there exists a value x. I mean, that is, you have chosen. You have chosen, that's also a process, but you have to choose a value x, and for which you get these two partitions. And then in the next, you have basically you are forming two nodes, and you can find easily check that all of them are positive. So you can declare it as a leaf node, and you did not proceed for splitting. But you find that this is a mixed region, so you need to split it. So now this becomes your input samples, right? So this becomes your input samples. So in these input samples, both positive, negative is there. And by some consideration, once again, you have selected the attribute 1. So again, in the second stage also, you have selected this attribute 1. And then you consider, say, this is the attribute value, say y, where you have you are making a split. Fine. Once again, you know that if the value is greater than y, then this is the region. If the value is less than 1, this is less than y, this is the region. And there you have found all of them are negative in this region, so it has become a leaf node. So you consider that's a negative. So leaf node, so you need not split it. But this one is a mixed. So now this region is the new set of input set for this node, where you find it's a mixed node. So you require a split. And here, when you once again you have to select one of these attributes, and as you can guess, which attribute you should select in this case. So
attribute 2.
Yeah, you should select attribute 2. That's right. So if I select attribute, in fact, that is what, and there is a position where the split takes place, and say uh, say this value is Z, and this is the position where the split takes place. So if the attribute 2's value is greater than Z, then you have a region. If it is less than Z, then you have a region, and it happens to be there here that both of them are pure. We call them pure node, right? If they are pure node, we declare it as a leaf node, and you consider that. So that is the level, that is the answer, and you stop further growing the tree. So this is the kind of mechanism using this kind of visualization we can explain, at least we can understand what way decision trees are formed. Only some of the things we have not yet uh, we have not yet discussed, and we should think about it, that how to select an attribute. That is the first question. So which attribute, right? So this thing, I mean, I will come to the next slide. It is written there, so let us not write here. So let me proceed. So which attribute, and at what values of the attributes if it's a continuous value. Otherwise, no, if it is a discrete value, then you need not bother. You have so many branches there. If it is continuous, you have to consider splits, even consider the number of splits also in that case. So you have these decision tree structures, and just in the diagram itself, it is mentioned. In fact, I have also shown some of the values which are shown here, and you see that there are split nodes which are called decision nodes, and there are there are decision leaf nodes where they are pure nodes, which are actually which has been shown here by different rectangular regions. So what should be your algorithm now? I have already given you enough enough cue to check what kind of steps you should take. So let me give you a bit more details. As you understand that you have started with an empty tree, then no, it has to be iterated, because at every iteration you are expanding the tree. You are finding out, you are at certain nodes, and you are finding out that whether that node should be split or not. And if it has to be split, then no, you split it, and you create few nodes. And no, you have to traverse through those nodes later on if they are not pure. So it is considered that find the best decision attribute for next node. So at every node, you consider what is the best decision attribute A, and you have to consider the corresponding input sample, data subset of that input training examples that is being considered in that node. So that is what that is defined by that node, and based on the levels of that distribution of levels in that input instances, you need to choose that which attribute, basically levels and values of the attributes, you should choose that. So you assign A as decision attribute for. Suppose you have some mechanism to get the best attribute. There is some measure, I will discuss it later on, depending upon the distribution, as I mentioned, the distribution of the instance values and also attribute values over the levels, also the levels. So it's a joint distribution of attribute values and levels. Based on that, we can decide which attribute should be taken for a split. And then suppose this attribute has been chosen, then you should assign a decision attribute for node. So now you create a node for that attribute value, and you are then there would be so many branches depending upon how many discrete values are there in the attributes. When you have considered this particular selection, there you have also taken care of that what are the attribute values, what is the distribution I told you. So from that characterizations, you can find out that what are the possible values, and what is the split finally. So based on those values, what kind of partitions you are getting. So all those things, no, you can propagate to the next levels of node. So for each value of A, create new descendant of that node, and also propagate the inputs the samples. That means transfer that subset of samples to those nodes. And you go, you iterate this process. So till you reach a leaf node. That means when the node is a pure node. So if training examples is perfectly classified, you stop. Otherwise, iterate over new leaf nodes, right? So here writing is little clumsy. Actually, when you reach a leaf node, means it has to be pure node. Otherwise, no, you characterize it as a intermediate node, and you start this process. You do this process. So you can grow tree just deep enough for perfect classification, which means that theoretically you can get, given a training example, you can get a decision tree which would be consistent with the examples. But as no, we have already mentioned that if there are errors, that would have huge repercussions on the generalization error. So that no, you have to also consider for a noisy samples. But so that is why usually in reality what happens that no, you assuming that your training data is error free is bit no, optimistic. Also sometimes what happens, we have also considered that no, probably approximately correct learning, that theory that there are even you have a consistent hypothesis, but your generalization error could be high. So it is not always preferred that no, you have to get a consistent hypothesis. So there are various reasons for which no, you should choose a certain kind of no, trade-off between allowing a little bit of training error and having also a less generalization error. We discussed also in the previous class about the way empirically you can find out a model, find out the best model. So this each decision tree is like a model. Depending upon different depth, different heights, different structure, each one is a different model. So you are not going to get an unique model. As you can see, this is not going to give an unique hypothesis once again. You can get a consistent hypothesis by selecting randomly any attribute also, without going for best decision tree, best decision attribute at that node. You can randomly choose, and you can do random split, and you can go on doing these things until no, you get at some finite iterations. You will stop because there would be everyone will be leaf node, and at the most, what happens that every path of the tree will consider only one leaf node. So, so that is the kind of situation you may have, but that is the I should say that's given the training examples, it's a much overfitting. It's a very much overfitting in that kind of situation. So so this is not exactly that is we are going to adopt in reality. We have to consider a certain kind of compromise between the training error and the depth of the tree, all those things. So the question is that if you are not going to do random selection, as I mentioned, though it can give a consistent hypothesis, but what should be the policy by which you are going to select an attribute? Why do you call it is the best? What is the criteria? So one of the things, as I mentioned, that no, we try to keep our hypothesis simple. That is that Occam's razor principle. That means the depth of the tree should be as small as possible, but it should capture largely the input space. So you try to get training error in a reasonable. You try to limit the training error in a reasonable range, but no, you try to get a depth which is the smallest step. Say, given some training error bound, can you get a smallest step? Something like that. No, you can pose it as a theoretical question given the data set for a decision tree. So under those constraints, so what kind of attributes you should choose to get the to reduce the size of the tree. So some of the that visualizations, once again, as you can see, that best attribute to split, intuitively we may consider that best attribute to split is as quickly as you get a leaf node or a pure node, right? That would reduce, that would keep your height of the tree small. So we are trying to find out that which partitions are going to give more or less reasonable chunk of partitions, chunk of regions in the space where there is a formation of a pure node, and accordingly all these corresponding attributes are selected, and corresponding decision nodes are created, and also leaf nodes are identified. So so that is the principle, that you try to form a tree with pure leaves as early as possible, so that it can keep your your hypothesis simple. The description of tree is also small. So naturally, pure leaves are preferred because now you have also training error 0 with the pure leaves for those data sets, and it's a kind of correct classification, but with respect to training error, you should with respect to training data set. As I mentioned that if it is a noisy data, maybe there are some errors. So we need to follow a greedy approach. Actually, this problem is NP hard. To get a minimal tree, minimal size tree, which will give you the consistent hypothesis, that is an NP hard problem. So we will follow a greedy approach in this case. What we will do that we can initially treat the entire data set as a single box, and then for each box, that means, see, this box is actually indicating a region in the input space. So if I assume your input space is a continuous valued, real valued input space, and then you can perform discretizations on that. But that box is some kind of hypercube or hyper rectangle in that input space. But it need not be always you should view it like this. It could be a set of discrete values. So box is a collection. So it's a kind of partitioning of set where you may not have any kind of ordered structure in your input space. Simply you have set and subsets. So that is the kind of ordering you have. So you consider that initially you have the whole set, and then when you are partitioning it, then you will have disjoint subsets, and which will cover the whole set. So it's a partition in that case. So at for each box, choose a split with an attribute that reduces its impurity. So our idea is that I would like to make this box as pure as possible, but what I'm getting at hand, that is not a pure. So I will first check whether it is pure or not. If it is pure, I can declare, okay, fine, it's a leaf node, let us not split. But no, if it is not pure, that means there are mixed levels, then we try to choose that attribute which will get me a split where you should have a reasonable size of a box which is pure. I mean, if you get that is preferred, and try to have a degree of purity in that sense. So it may not be perfectly pure, but suppose majority of the samples, it's a skewed, I should say, it is a skewed box. Many of them are of same types. So you can identify them, and you prefer those splits because in the next iteration, probably you take less number of iterations to convert it into a set of pure collections of subsets. So that is what. So we are going to consider a measure of purity or impurity, whatever way you call it, and depending upon that measure, we will choose an attribute. We'll choose an attribute which will either maximize that measure or minimize that measure. If it is a measure of purity, so we'll try to see that attribute value, that means is this measure of purity is with respect to the split. Say you have a measure of purity of the input box, original box at hand at any node, and then you make a partition and you consider a measure of purity with respect to that partition. Now you compare these two. You compare these two measures, uh, check the improvement. So you choose that attribute which will have the most which will give you the most improvement, the best improvement in that case. So you split the box having highest reduction in impurity. That is what I was mentioning. That if it is a measure of impurity, then no, you choose that attribute which will have the highest reduction of impurity, and then you split the box. Uh, and you go on doing these things. So this is the approach that we will be considering while growing a decision tree. And naturally, as I mentioned, that if you find your box is a pure box, you should stop growing it. So these are the steps. So now I will discuss that what kind of measures you can think about when you are considering this measure of purity or impurity. Um, you considered 64 examples. So these example set were earlier shown, and if you remember, there is a table which describes the conditions of the day. Um, I can go back and show you. It will take a little bit of time. I think so. This is a table, right? So this is a table, and you have so much level, but no, I think you have more number of tables. It is just an examples. Consider, I think that is an hypothetical situation. It must be an hypothetical. There is only 14 examples, and here you are considering 64 examples. I'm sorry. So it is not that table. It is some hypothetical situation where you have two attributes, A1 and A2. And you have 64 examples, 29 of them is positive, and say 35 of them is negative, right? And attribute sets have, say, all are binary valued attributes. Say A1, it has two values, and we are representing them by T and F, so representing true and false kind of binary levels. Similarly, A2 is also attribute which also has two values. So these are all two valued attributes, and there are 64 examples, out of which 29 is positive and 35 is negative. That is the context. Now I will give you some scenarios. Let me use my here. Let me use the pen. Let me show this partition. See, you consider this a first scenario, right? This is the first scenario. And this is actually the other scenario, which is not related with the, these are independent two scenarios. Now, in this scenario, so as I mentioned that at the starting, you have this scenario. So you have 29 positive and 35 negative. Now you check that when you have the attribute A1 and you find out your, consult your training examples, from that set, you have observed that if the value is true, then then it gets, say, subset of the training examples. When for A1 equal to 2, you select all those examples where A1 equal to true, A1 is T. Then from there, the distribution of these output levels is like this. You have 25 positive and 5 negative. So remaining for A1F, naturally, there is a 29 positive here. So here you have 4 positive and then 30 negative. You can see it's quite skewed. So it is this partition looks to be favorable partitions with A1. What happens to A2? Now in A2, you get a partition with 15 positive and 19 negative, and correspondingly for F, you have 14 positive and 16 negative. Now, just by looking at this value, you can guess that which attribute should be selected. but what should be the mathematical measure, right? So
A1.
which, yeah, A1, that's what I'm saying, that no, it is very clear with this skewed distribution, with our intuitive reasoning, we can choose A1, but what should be the mathematical reasoning? What should be the mathematical measure? That we'll discuss. Let us consider the second scenario. I told that these are all independent, so don't see any connection between this. So you have still you have 64 examples, and but you have a different distributions of attribute values with the positive and negative examples. So here the distribution is that you have 21 positive, 5 negative, then 8 positive, 13 negative, right? So still no, you have skewed distributions, not bad. And here no, you see 18 positive, 33 negative, um, less skewed, huh? But here you see 11 positive and 2 negative. So which is I should say more skewed. Only the which is quite highly skewed, I should say. 11 positive and 2 negative. Now in this scenario, which one you should think which one should be taken?
Sir, in case of A1, it is I think positive values are skewed at the left hand side, and so A1 should be taken.
Any other contention? Okay, so I should say it is there are some situations where it is very difficult to tell. Huh? So this is a situation where there is some kind of competition is still there. It is not very clear. As the previous example, you could clearly say, no, A1 gives you skewed distributions with in both the partitions. Um, Here, A1 gives somewhat skewed distributions in both the partitions, but A2 gives in one partition it is not at all skewed, I mean less skewed, and in second partition rather the skewness is quite high. So what we'll do, we'll define a measure using your mathematical logic, and from that measure we'll decide. So simply you have to compute, and no, the values will just give you the degree of impurity. So you compute the degree of impurity of this this node, then compute the degree of impurity of this node and this node, and then you aggregate them. You can aggregate them to a common degree, to a measure of degree of impurity of this partition. Then you consider what is the improvement, what is the gain. So gain would be difference between these two. So you compute all these gain, and wherever you get the maximum gain, you choose that attribute. So let me proceed, and I will explain this part. So this is the measure many of you know. Have you heard of entropy? Is there anyone
Yes,
who has
sir.
not?
Yes, sir.
Yeah. So what is entropy? How do you measure entropy?
Degree of randomness of any sample or space.
So what do you require to measure this degree of randomness? Or here it is saying it is
Probability.
probability.
Log of probability, inverse of probability of occurrence of an event.
I need more precise answer.
We
Like
should, we
it's
should
expectation of log of 1 by probability, something of that kind.
Good. So you are basically remembering the expression,
Yeah.
but actually you require probability distribution. You require probability distribution of the data, and so what you are saying, that is true, that is correct. So given that distribution, then you find out that expectation of log, right? So what? Let me proceed. So one of the interesting no information theoretic interpretation of entropy is that if I am going to encode the corresponding information whose data, rather I should say data here, whose distribution is given by, whose probability distribution is known, and which occurs with a probability p, right? then I need a need a coding. So more. So the question is that less the probability, higher the information you have. So if you already know some fact, and if I provide you, it is not an information to you. If I tell you that Trump is the president of USA, I'm sure in all probability you know that. But if I ask you who is the president of Zimbabwe, and if I give you information, probably no, many of you do not know. And the probability of knowing that is much less. So you get more information, right? So so this is something which is which measures, as I was mentioning, that less probable is an information, is a data. It carries higher information, and which means that to represent that data, you requires more number of bits. There is information theoretic interpretation. So I'm not going into details of those things, but let us understand this mathematical representation. Somebody has said that log of inverse of probability. Do you think that is what is represented here?
Sir,
That
that is
red,
Yes,
that red
yes,
color? Yes.
yes,
Right?
yes. It's same because if we take minus sign
yes,
inside, then it becomes 1 by p.
Right. Very good. Very good. And why the value 2 is chosen?
sir. Binary
Binary
zero.
representation. So the coding assumes the coding is you are like the way you encode a data, any data, it's basically a binary representation, binary string. So you require that one. It's a huge, it's a great characterizations. And who is the person who has provided this information theoretic interpretations, and do you know his name?
Shannon.
Shannon.
Yeah, Claude Shannon, right? So fine. So let us see that how actually this is measuring. This is measuring impurity. So what do you expect? Suppose your data has more entropy. Now I can say data has more entropy. Entropy with respect to what? With respect to class levels. Entropy, your data means, say, your instance, they have class levels. So it is the distribution, class level distribution over the instance space. Is it clear?
Yes,
That
sir.
means you have positive example, negative example. Given the input space, you can find out how many of them are positive, how many of them are negative. You can find out then what is the probability of a sample being positive, what is the probability of a sample being negative. I hope it is clear to all of you. Though I will take a brief about probability, but I am expecting, since this probability thing, many things should be clear to you. And otherwise, please read some book on probability and statistics, all basic books, etc. Huh? So, what was my question? Can you repeat? I just forgot. What is the question I asked? How entropy measures impurity? How it is related? Anyone?
Sir, if all events have probability of occurrence is same, so there is the highest chance of the uncertainty there. But if the probability, there are only two events and one occurrence is fixed and other will not occur, that is also fixed, then the entropy in that case will be lowest. So that way we can define it in the range.
No. In your context, when I am saying that impurity, a node is degree of impurity, how it is related with entropy? Can I say higher the entropy, then what is? Higher the entropy, your
Lower
degree
the
of
purity.
impurity would be,
High.
your
Impurity
actually,
will increase.
yeah, your impurity will increase or decrease?
Increase.
Increase.
Increase, sir.
Yeah. Higher the entropy, higher the impurity. That is fine. So, what should be the, suppose I have, in this case, say I have two levels, say P1 and P2. Sorry, I have two levels, 1 and 0. And 1 occurs with a probability of P1 and 0 occurs with a probability of P2. Please have your book, because I'm sorry that I'm not able to use Blackboard and other things, and it's difficult. I have some constraint. So please write it, and I'm asking you, then you can answer me. So you have the as I mentioned, P1 represents the probability of the level being 1, and P2 is the probability of level being 0. Fine. Can you tell me what is the entropy of that distribution?
Hello, sir.
Yeah,
Is it P1 log of 1 by P1 plus P2 log of 1 by P2?
exactly. Thanks. Has everybody understood? It is basically, somebody told already, weighted average of this, log of 1 by P something, weighted average of this information, this optical here. So what is weighted average? What is the weight? Weight is the probability here. And what is the sum of weight? P1 plus P2 equal to 1. Is it clear now? So entropy is actually weighted average of these optimal length codes. So let me just give you this expression. I hope here we have used a different representation. Instead of P1 and P2, I have used P positive and P negative, like subscript symbols. Is it clear?
Yes, sir.
Okay, so it can be also generalized to more than two values. I hope that is understood also. If I have a distribution, if simply generalize it, I have n values, so P1, P2, P3 to Pn. That means those are the probabilities, and then it will be sum of Pi log Pi, keep minus outside sum, right? So that is what is your entropy. That is the weighted average of all such optimal length codes. I mean, optimal lengths, I should say, of their code. I hope this is fine. Any question? So we said that entropy can be viewed like this, and these are certain examples. Say P plus 1, P plus 0. If I just specify P plus, that means I am specify also P minus for a two valued cases. That is clear, because 1 is P plus means P minus should be
1 minus that.
right.
0.
So you get sum over that. What is the highest entropy for a two valued function? What is the highest value? Can you tell me?
Log 2 of number of
Log 2 of 2.
how many symbols are we taking, then log 2 of
Yeah.
it.
Yeah, but no, there is a very easier. So actually, highest probability occurs when all are equally probable. Intuitively, also you can say all are equally probable. That means you have the highest information. So when all are equally probable, it is half, 1 by 2, right? So it is
Yes.
basically log 2 of 2, which is equal to, what is the highest value? Log 2 of 2, what that value? That is equal to 1. Yeah, and what is the lowest value?
0.
Right. So for a two valued functions, value lies between 0 to 1. Can I take 5 minutes more, or are you time pressed? Uh, is it okay?
Yeah.
Yeah, because no,
Yes.
I will just complete after going to the next slide. Huh? So if you have, suppose, k values, if you have k values, what is the highest entropy? K attribute.
Log K.
Log k base 2. The same, huh? Because 1 by k, all should be 1 by k. That is the uniform distribution. Then you get the highest entropy. So with this, let us consider, I mean, this will show you all those results. That's why I was interested to take some more time from you. And as you can see that, let me once again use that split, because these are two independent cases. Upper one is, so you see that here entropy was 0.993. That is the original entropy when you get at this node. And then with this split, you get 0.650, 0.522. So what should be your gain? Now you should not add them. There should be like, no, you have the weighted average of those things. Here also it should be weighted average of entropies. And how the weights should be given? Weight should be given by the fraction of samples of the total coverage of your parent node. So this weight is 30 by 64 and this weight is 34 by 64. Fine. So 30 by 64 into this plus 34 by 64 into this. So that would give you the corresponding weighted average of entropy. And if you take the difference, that is your gain. Similarly, you do these operations. Here you can see naturally these numbers are large. We already guessed. And you can see this number is quite small, but maybe, as you have said correctly, that this attribute is preferred. Let me say, so it shows the information gain as I mentioned. So these are the gains. These are the gains. In fact, I mean, the person who told intuitively by looking that A1 should be taken for both the cases is correct. It is also a bit clear, but still there could be sometimes a lot of contentions. In fact, there are. I hope today I will stop here. And this is the policy of choosing an attribute. And things, that is what you require for forming a decision tree. All other computational steps are known to you now. And this is that. So I will take questions from here. Any question? Another
Sir,
5
to
minutes.
calculate the entropy of topmost E of S equals 0.993, why are we taking weighted average when we have directly the amount of positive and negative samples?
No, A1 for A1 we are not taking weighted average. There is only one partition. When you have multiple partitions, like here you have you have two partitions. Now you have to get average entropy of this partition. Here you have only single. In a parent node you have a single partition. It is just the entropy. There you are taking. So this fraction is the fraction of this by, I mean, fraction from, so it is basically 30 by 64, this fraction for
Got
this
it.
one. Yeah?
Got it. Yes.
Okay. Okay. Any other question? Okay, so if it is fine, so tomorrow at 8 I will start. Yeah.
Sir, kindly
Attendance.
download the attendance.
Attendance, right.